this video, we will discuss about the driving force of the reactions. But before talking this topic, I would like to explain the second law of thermodynamics. The no spontaneous transfer of heat from cold region to hot region. Okay, it couldn't be occur. It couldn't occur. Okay, so this is the example. You never saw the water change to the low temperature. Change from low temperature to hot temperature, high temperature. Always water's temperature change to the cold one. Why? The heat is total kinetic energy of molecules. This is very important concept. That means in the high temperature, there are a lot of molecules, with the momentum. And low temperature, there might be a small amount of molecule with the no momentum, as shown here. So always we think that the total kinetic energy of molecule in the container is larger in the case of the high temperature one. And total kinetic energy means the number of molecules and momentum of the molecules. So you can imagine that the container divided into two parts with some, shield, and the left-hand side have the hot region, and the right-hand side is cold region. Of course, the hot region have a large momentum of the molecules shown here, and large momentum molecule go into the cold region after removing this, shield. Then heat, the Q, always transfer from hot to cold region because momentum of the molecule is larger here, so easily access to the cold region. But the molecule in the cold region, the momentum is very small, so very slowly go into the hot region. But hot molecule can easily go into the cold region, and this is spontaneous process. Okay, no energy added, but it occurred. So this is very important explanation to understand the second law of the thermodynamics. And in this case, no delta H need to push this process. That is very important. We do not see any heat from this system, just mixing. Okay, so we need to use another state variable, which is entropy. The entropy. Okay, so here you can see the definition of the entropy. S. Again, I would like to say that the second law of thermodynamics, any spontaneous process increases the disorder of the universe. And this disorder of the universe is actually the entropy. And entropy can be expressed by equation as shown here. S is the entropy, and entropy equal Q over T. Q means the heat energy, and T is the temperature. And importantly, delta H means the initial state of Q here, initial state of the temperature here, minus final state of Q here, and final state of temperature here. And if this value is larger than 0, the change should occur spontaneously. Okay, And that means, in other words, if you can see this is the container divided two region, hot region and cold region. The temperature of hot region is T1 and T2 means the temperature of the cold region. And delta is mixed. I mean if you remove this shield by your hand, and you can mix the hot region and the cold region, and what's happened, you can see the S1 and S2. You can add these two part. Delta S1 means the delta S in the hot region, and delta S2 means the delta S in cold region. So in that case, this could be equation of the delta S, because the Q should be the same. You can remove the heat here and add the heat here. So the removing heat should be the minus at the hot region, and adding heat should be Q here in cold region, and this value is completely same, and temperature is different. And this equation can express as shown here. So this value should be over 0. That means T1 should be bigger. Okay, so this is another intuition of the second law of the thermodynamics. And importantly, the delta S, I mean disorder of the universe, should be increased. This is important. But the disorder is sometimes confusing, so you need to think about the disorder carefully. And if you say that disorder in the physical chemistry, you need to be careful to use the disorder word, because sometimes your mother said that you need to clean up your room, So some teacher says that the messy room is one of the results of the second law of the thermodynamics. But that explanation is not true. This is clean room, okay? And this is messy, dirty room, okay? So these two rooms are actually the same entropy. Delta S is almost 0, because these two rooms is actually different microstate, but same macrostate. The table and books and some chairs, the components are same. In that case, the what a messy state in your dirty room, but the component is the same. That means the disorder is the same. Okay, so in that case, these two rooms should be the same entropy. But if you clean up your room and put the flowers with vase, in that case the components is much larger than the clean room before, then the number of possible states is increased. In that case, the delta S should be larger than the before cleaning. Okay, so the number of components, I mean the number of molecules, is very important to determine the disorder of the universe in the system. Okay, so you need to think about the number of molecules and also the temperature. Temperature is very important. The higher temperature is very, unique. How can I say? Higher temperature is very, important for the disorder. So for example, hot clean room with flowers. This is the higher disorder state. I mean the delta S should be larger than 0 in this case. And after thinking about this entropy or disorder, you can think about the reaction using entropy versus enthalpy. Okay, so the chemical reaction is actually a change of the state from the reactants to the products. And you can discuss about the reaction by the use of the driving force, I mean the free energy of the reaction. And delta G equal delta H minus T delta S. This is very important equation. And this part, I mean the delta H is actually the heat change of the reaction. If you obtain the heat energy after the reaction, this reaction is exothermic under constant pressure. Okay, and in other case, if you need to add heat. How can I say? If you feel the cool down of the reaction system, in that case, the endothermic reaction. This is the change of the heat by changing the chemical bonding or something. Okay, and this part, T delta S part, is also the heat energy under constant pressure, a constant temperature. Constant temperature. Here you can see the equation of the delta S, and if the temperature is the same, in that case you can express the this delta S as this equation. That means under constant temperature, T delta S should be the Q prime as shown here. And these change of the heat before and after the reaction, this is our kind of energy under constant temperature, and that coming from the change of the disorder of the system. And this equation is very tricky, but if you think about this reaction, this equation can completely understood. Okay, so please think about the combustion of the hydrogen to obtain the water. This reaction is actually enthalpically favored reaction. I mean the bond energy of the change can you can calculate the bond energy change or something by the use of the table. In that case, you can obtain the delta H is minus. That means the exothermic reaction. But please think about the entropy of this reaction. You can count the number of molecules, 1, 2, 3, 3 molecules here. On the other hand, there is 2 molecules here. The number of molecules change from 3 to 2. And furthermore, there is 2 types of molecule, hydrogen and oxygen. And there is only 1 molecule, just hydrogen. Then, disorder of the state, universe, change to the, minus. I mean, delta S is negative in this case, from the H2O2, H2O2 to H2O. In that case, this reaction from the reactant to the product is entropically unfavored reaction. Instead of that, from water to the H2NO2 is entropically favored reaction. In that case, we need to think about this kind of, movement of the ball. This is ball, and this is the ballet. Maybe some of you have experienced the experiment of the physics, the ball movement, to feel the some potential energy of the ball. And this state is the reactant, okay? And this ball can move from this part to the bottom using the potential energy described as the delta H. Okay? And after that, you need to add some heat to, go up to this, stage by the use of the minus T delta S, because this is entropically unfavored reaction. Okay? Enthalpically favored, but entropically unfavored reaction. Then you need to calculate the delta G by the use of the delta H minus T delta S to evaluate the spontaneity of the reaction. Okay? Then this G is very important value, so we say that this gives free energy determine the spontaneity of the reaction. And we say that this delta Z equal to the driving force of the reaction. So actually, this offset of the energy is the driving force. Delta H is a main part of the driving force, but you need to pay some energy to, struggle to the, entropy problem. So important part is here, the spontaneity is not determined by delta H, but by delta Z here. So if you want to evaluate the spontaneity of the reaction, you need to calculate the delta G shown here. And sometimes we use the spontaneity of the reaction by the use of we discuss the importance of the delta S by the use of the entropy controlled reactions. Okay? Most of chemical reactions controlled by delta H. So exothermic and endothermic estimated using bond energy is quite useful. But sometimes an endothermic reaction occurs spontaneously. So here I'd like to show you the practice. This could be the assignment of this, assignment today. And you can see this chemical reaction. This chemical reaction is very, very interesting because this reaction proceeds very smoothly, but endothermic. So very cold, of the glass of the beaker was, if you touch the, reactor, you can feel very cold reactor under the condition of this, reaction. And actually the delta H equal to 166 kilojoule. That means endothermic reaction. Okay? And delta S is 594 joule per Kelvin. And temperature is 25 degrees C. So please calculate the delta G and check the spontaneity This is typo. So of the reaction, okay? And in this case, this reaction is actually the entropy controlled reaction. So you need to think about this kind of, figure to understand the spontaneity of this reaction. Actually, instead of the delta H, in the case of this reaction, this ball, drop down to this valley bottom by the use of the Q prime, I mean the minus T delta S. Okay? And after that, you need to pay a large delta H. This is plus, so you need to pay this energy to get here. Okay? So in the case of this reaction, the delta H, delta G can calculate by adding delta H minus, the minus T delta S, okay? So you can easily calculate by the use of these values to obtain the delta G. So this is the assignment of today. Okay, so let's call it a day and see you next week.